Hey, what's up, everybody? Welcome to physics. I don't know why the board's so yellow. It's just yellow. Normally, I'll be using a better camera than this, but had some technical problems today, so I'm just shooting you something real quick on my cell phone. This isn't going to take long. So this is the beginning of the first chapter notes. I just want to show you just the physics stuff we talked about today. Of course, there's a couple of things on the metric system I've asked you to look at and to do. And the way you turn those in is just take a picture, turn it in. You've already been doing this. So first few slides you can look at, it's just, hey, we try to do things through science, scientific investigation. And then we're going to be using these units from the metric system, okay? And here are the units. There's a video on metric units already, so I'm not going to go over these, but you know, kilo means 1,000. Our base units, so this would be kilometer, the base unit would be meters, and milli would be 1/1000th. Centa is 1/100th. So a centimeter is 1/100th. A meter, it's the stuff you've probably already gone over. Just for the fun of it, let's say, I'm going to make this super quick. Let's say you had a desk, K, H, D, space, D, C, M. If you had a desk that was 138 centimeters long, that means the 8 from the one place would be under the C on this little chart. So your desk, if it's 138 centimeters long, that means meters will be our units here, right? Then that would mean it was 0.00138 kilometers long. Does that make sense? Good. All right, done talking about it. That's in a different video, and you'll get that information elsewhere. All right, talk about significant figures a little bit when I see you in person. All right, so here's some vocabulary. Motion diagrams, that shows a body in motion. A particle model just represents the body that's in motion as just a dot, okay? I'll talk to you about that in just a second. Magnitude is just a word that means the amount. So what is the magnitude of the force? It just means what's the force, okay? If something is pressing on something with 10 newtons of force, then the magnitude of the force is 10 newtons. Okay, vectors are arrows that have numbers attached to them. And if you have two different arrows going in two different directions, then the resultant will be the sum of both of those arrows. So here's an example. Let's say something is pushing with 10 newtons of force up, and something else is pushing with 10 newtons of force sideways. Then the resulting motion will be like that. That's the resultant. These two are vectors, okay? And we could very easily solve for how many newtons of force by using, guess what? That's right, Pythagorean theorem. Pythagorean theorem. And we'll cover that later as well. When we talk about scalars, those are numbers that don't really have direction, like seconds. 7 seconds, that's a scalar number. This is what I'm looking for. All right, so yes, I'm going over this quick because no, you're not in a vocabulary class. I just need you to kind of understand some of these when we start doing some math. All right? There's several YouTube videos. This is a good YouTube video on vectors. Now let's take a look here. This is a motion diagram, but it's particularly a particle diagram. I asked students, hey, what is being tossed up in the air here? And they said, well, it's a ball. Well, no, it could be an axe, or it could be a matchbox car, or it could be a ball. But whatever the object is just represented by this dot, okay? And then all these arrows, notice they're the same length. So these arrows are qualitatively the same. Since they don't have a number, I wouldn't call them quantitative vectors. These are qualitative, all right? So this little a means acceleration. So you may say, oh, well, that A, what does that A stand for? Yeah, gravity, acceleration due to gravity. And notice something you can infer from this is that the acceleration towards the earth due to gravity for the ball or whatever it is that's being thrown up in the air is constant. It's the same. Does that make sense? All the arrows are the same. It's a qualitative particle model. What's something else we could assume by looking at this graph? Well, we can assume that the object flew in a parabola. You can assume that because here it goes. It's landing further away from him. And the next thing you would have to assume, or you can infer from looking at the graph, is that as this object goes up, its vertical motion slows down because the dots get closer together. And as this object falls, its vertical motion, or its velocity towards the earth, increases because the distance between the dots becomes greater. These are things we need to look at. Something I try to drive home in physics class in the first day or two is that the math in physics is not hard. Almost all the math we'll do in this entire course is Algebra 1. But it's understanding what little math problems to apply and understanding things that you need to infer. That's what physics is. All right? Now these are actual motion diagrams because we can see that these are people running. Now if we just put a dot here and had dots instead of people, then they'd be called particle diagrams or particle models. So that's how simple that is. All right. Now in these pictures, in each one of these pictures, we have the same runner, okay? And there's a camera, and it takes a picture once every second for 5 seconds. So let's take a look at A. Boom. Okay, we can assume from A that for 5 seconds, this person stayed at the starting line. All right, what can we assume about B? If this is, say, a cross-country race, what can we assume about B? Is this the beginning, middle, or end of the race? It's the middle of the race. In 5 seconds, boom, 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 boom. This person's running a constant velocity because the distance between the people are the same. Take a look down here at C. Yeah, this is the beginning of the race. Go. And then the person, boop, 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 they get going faster and faster. And then obviously D is the end of the race, because we'll say they cross the finish line right here and then they're slowing down to rest. These are little things, these are motion diagrams. This is a photo taken, I don't know, every quarter of a second for a couple of seconds. And this person, you can see what they're doing. You can see their motion, it's inferred, a lot of things. And we can see that she's moving from left to right with a constant velocity. Even though she's spinning or turning or doing whatever dance move this is called, she's moving from left to right with a constant velocity. What about this dude right here? All right? We can see this is a motion diagram, and this is the beginning of a race. If we represented this dude as a particle, then we could put a dot, 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 and then look, this dot's getting further away. So this guy is actually speeding up. Does that make sense? The distance between each dot is growing. And that's all we covered on day 1. So I hope you enjoyed that, and that's literally it. That's day 1. Of course, you have some metric system work to do today. The work is due tonight by midnight. You need to do your work every day. That's in the other videos. See ya.